A coupling is a mechanism for connecting rolling stock in a train. The design of the coupler is standard, and is almost as important as the track gauge, since flexibility and convenience are maximized if all rolling stock can be coupled together. The equipment that connects the couplings to the rolling stock is known as the draft gear. Nomenclature: the different types of coupling do not always have formal or official names, which makes descriptions of the couplings in use on any railway system problematic. Buffers and chain. The standard type of coupling on railways following the British tradition is the buffer and chain coupling used on the pioneering Planet-class locomotive of the Liverpool and Manchester Railway of 1830. These couplings followed earlier tramway practice but were made more regular. The vehicles are coupled by hand using a hook and links with a turnbuckle that draws the vehicles together. In Britain, this is called a screw coupling. Vehicles have buffers, one at each corner on the ends, which are pulled together and compressed by the coupling device. This arrangement limits the slack in trains and lessens shocks. The earliest buffers were fixed extensions of the wagon frames, but later spring buffers were introduced. This coupling is still the standard in European countries. Link and pin. The link and pin coupling was the original style of coupling used on North American railways. After most railroads converted to semi-automatic Janney couplers, the link and pin survived on forestry railways. While simple in principle, the system suffered from a lack of standardization regarding size and height of the links, and the size and height of the pockets. The link and pin coupler consisted of a tube-like body that received an oblong link. During coupling, a rail worker had to stand between the cars as they came together and guide the link into the coupler pocket. Once the cars were joined, the employee inserted a pin into a hole a few inches from the end of the tube to hold the link in place. This procedure was exceptionally dangerous and many brakemen lost fingers or entire hands when they did not get them out of the way of the coupler pockets in time. Many more were killed as a result of being crushed between cars or dragged under cars that were coupled too quickly. Brakemen were issued with heavy clubs that could be used to hold the link in position, but many brakemen would not use the club, and risked injury. The link and pin coupler proved unsatisfactory because it made a loose connection between the cars, with too much slack action. There was no standard design, and train crews often spent hours trying to match pins and links while coupling cars. Crew members had to go between moving cars during coupling, and were frequently injured and sometimes killed. The links and pins were often pilfered due to their value as scrap metal, resulting in substantial replacement costs. John H. White suggests that the railroads considered this to be more important than the safety issue at the time. Railroads progressively began to operate trains that were heavier than the link and pin system could cope with. An episode of the 1958 TV series Casey Jones was devoted to the problems of link and pin couplings. Albert Coupler. To avoid the safety issues, Carl Albert, then director at the Krefeld Tramway, developed during the 1920s the Albert coupler, a key and slot coupler with two pins. Cars to be coupled were pushed together, both couplings moving to the same side. One pin was inserted, then the cars were pulled to straighten the coupling and the other pin inserted. This operation required less exact shunting. Due to the single-piece design, only minimal slack was possible. The system became quite popular with tram systems and narrow-gauge lines. During the 1960s most cities replaced them by automatic couplers. But even in modern cars, Albert couplers get installed as emergency couplers for towing a faulty car. The Miller hook and platform, the link and pin was replaced in North American passenger car usage during the latter part of the 19th century by the assemblage known as the Miller platform, which included a new coupler called the Miller hook. The Miller platform was used for several decades before being replaced by the Janney coupler. Norwegian. Norwegian couplings consist of a central buffer with a mechanical hook that drops into a slot in the central buffer. There may also be a U-shaped securing latch on the opposite buffer which is fastened over the top of the hook to secure it. The Norwegian is found only on narrow-gauge railways of 1067 mm, 1000 mm or less, such as the Isle of Man Railway, Western Australian Government Railways, the Western Eog Railway and the Welsh Highland Railway, Tanzania, where low speeds and reduced train loads allow a simpler system. The Norwegian cupola allows sharper curves than the buffer and chain, which is an advantage on those railways. On railway lines where rolling stock always points the same way, the mechanical hook may be provided only on one end of each wagon. Similarly, the handbrake handles may also be on one side of the wagons only. Norwegian couplings are not particularly strong, and may be supplemented by auxiliary chains. Not all Norwegian couplings are compatible with one another as they vary in height, width, and may or may not be limited to one hook at a time. ALll coupling previously used in South Africa railways prior to World War II. Automatic couplers. There are a number of automatic train couplings, most of which are mutually incompatible. January coupler equals. Later Master Car Builders Association coupler, now AAR coupler. Also commonly known as a Buckeye, knuckle, or alliance coupler. The AAR-APTA Type E, Type F, and Type H couplers are all compatible Janney couplers, but used for different rail cars. The knuckle coupler or Janney coupler was invented by Eli H. Janney, who received a patent in 1873. It is also known as a Buckeye coupler, notably in the United Kingdom, where some rolling stock is fitted with it. Janney was a dry goods clerk and former Confederate Army officer from Alexandria, Virginia, who used his lunch hours to whittle from wood an alternative to the Lincoln pin coupler. The term Buckeye comes from the nickname of the U.S. state of Ohio, the Buckeye State, and the Ohio Brass Company which originally marketed the coupling. In 1893, satisfied that an automatic coupler could meet the demands of commercial railroad operations and, at the same time, be manipulated safely, the United States Congress passed the Safety Appliance Act. Its success in promoting switchyard safety was stunning. Between 1877 and 1887, approximately 38% of all railworker accidents involved coupling. The percentage fell as the railroads began to replace link and pin couplers with automatic couplers. By 1902, only 2 years after the SAA's effective date, coupling accidents constituted only 4% of all employee accidents. Coupler-related accidents dropped from nearly 11,000 in 1892 to just over 2,000 in 1902, even though the number of railroad employees steadily increased during that decade. When the Janney coupler was chosen to be the North American standard, there were 8,000 patented alternatives to choose from. The only significant disadvantage of using the Janney design is that sometimes the dryheads need to be manually aligned. Many AAR coupler designs exist to accommodate requirements of various car designs, but all are required to have certain dimensions in common which allow for one design to couple to any other. The Janney coupler is used in the United States, Canada, Mexico, Japan, Taiwan, Australia, New Zealand, South Africa, Saudi Arabia, Cuba, Chile, Brazil, China and elsewhere. Changes since 1873. Basley coupler Willison SA3 coupler equals. The Russian SA3 coupler works according to the same principles as the AAR coupler but is incompatible. It was introduced during the rebuilding of the railway network in the Soviet Union after the Second World War and has since been used on the whole broad-gauge network, including Mongolia. It is also used on the standard gauge networks of Iraq and on Malmbanan in Sweden for all trains. Russian trains are rarely longer than about 750 m and rarely exceed a maximum tonnage of about 6,000 t, so it is not clear what potential load these couplings are capable of. The trains on Malmbanan are about 8,000 t. The force to break the SA3 coupler is about 300 tf. The maximum allowed tractive effort to the SA3 is limited to 135 tf by Russian white papers. The proposed European automatic coupler is compatible with the Russian coupler but with automatic air, control and power connections. Implementation is permanently delayed except for a few users. See Europe below. The SA3 resembles a left-handed fist. Some 610 mm gauge cane tramway vehicles in Queensland have been fitted with miniature Willison couplers. Unicoupler Intermat Unicoupler has been developed by No Company from Germany in the 1970s and is widely used in Iran in freight cars. This type of coupler is compatible with SA3 and Willison couplers. The unicoupler is also known as AK69E. The unicoupler was the West European development. It was developed in parallel with a compatible East European counterpart, the Intermat coupler. CAKV. The CAKV coupler is a newer compact Willison coupler developed by Favely Transport. It is mechanical fully compatible to the SA3 coupler and the unicoupler, and if additional buffers are mounted it can be coupled with the conventional European screw coupling as well. Multifunction couplers. Multifunction couplers are fully automatic couplers that make all connections between the rail vehicles without human intervention, in contrast to auto-couplers which just handle the mechanical aspects. The majority of trains fitted with these types of couplers are multiple units, especially those used in mass transit operations. There are a few designs of fully automatic couplers in use worldwide, including the Scharfenberg coupler, various knuckle hybrids such as the tight-lock, the wedge-lock coupling, Delner couplings, BSI coupling and the Scharker-Tomlinson tight-lock coupling. There are a number of other automatic train couplings similar to the Scharfenberg coupler, but not necessarily compatible with it. Older U.S. transit operators continue to use these non-Janney electro-pneumatic coupler designs and have used them for decades. Gallery Westinghouse H2C The Westinghouse H2C coupler is currently used on the R32, R42, R62, R62A, R68, and R68A class subway cars of the New York City subway. The A ends of the cars typically have the Westinghouse coupler and the B ends use either a semi-permanent drawbar, or a Westinghouse coupler. WABCON type The WABCON type coupler was first developed for the prototype Pittsburgh Skipbus system, with the initial Model N1 is applied only to the 3 Skipbus cars. The updated Model N2 with a larger 4-inch gathering range was first applied to the new Airporter Rapid Transit cars on the Cleveland Rapid Transit line. The Model N2 used lightweight draft gear slung below the center sill, to allow for the wide swings required to go around sharp curves. This made the N2 unsuitable for mainline railroad use, so an updated version N2A was developed for that market. The first of these were fitted in 1968 to the UAC turbo train with 228 electrical contacts and the Bud Metropolitan EMU with 138 contacts. Starting in the 1970s, the N2A was fitted to the entire Scepter-Silverliner family of MEUs, the NJT Arrow series of MEUs and the Metro North LIRRM series of MEU rail cars. The N2 was also used by the PATCO Speedline, but was replaced due to issues with the electrical contacts. Later WABCO would create a new Model N3 for the BART system with a 6x4-inch gathering range which required a rectangular funnel. The WABCON type is sometimes referred to as the pin and cup coupler or spear coupler. Tomlinson The Tomlinson coupler was developed by the Ohio Brass Company for mass transit applications, but eventually found use in some mainline railroad vehicles as well. It consists of 2 squared metal hooks that engage with each other in a larger rectangular frame with airline connections above and below. Since the coupler's development, the manufacturing arm of Ohio Brass was purchased by WABCO, which now manufactures the line along with the N-type. The Tomlinson coupler is the most widely used fully automatic heavy rail coupling in North America, having been adopted by the DC Metro, MBTA, PATCO Speedline, SEPTA Broad Street Subway, LA Metro, Baltimore Metro, Miami Metro, MARTA Rail and the New York City Subway for its R44 per Rankine 46 fleet and all modern classes starting with the R142. For applications outside of rapid transit, the coupler had to be significantly enlarged to meet the increased strength requirements, first appearing in this capacity on the Bud Metroliner and later on the Illinois Central Highliner fleet. Its relative lack of strength is one reason the N-type has been more successful in the mainline railroad arena. Scharfenberg coupler The Scharfenberg coupler is probably the most commonly used type of fully automatic coupling. Designed in 1903 by Karl Scharfenberg in Karl Paragraph Nigsburg, Germany, it has gradually spread from transit trains to regular passenger service trains, although outside Europe its use is generally restricted to mass transit systems. The Shaka coupler is superior in many ways to the AAR coupler because it makes the electrical and also the pneumatic connections and disconnections automatic. However, there is no standard for the placement of these electro-pneumatic connections. Some rail companies have them placed on the sides while others have them placed above the mechanical portion of the Shaka coupler. The main disadvantage to the Schaffenberg coupler is its low maximum tonnage, which makes it unsuitable for freight operations. Small air cylinders, acting on the rotating heads of the coupler, ensure the Shaka coupler engagement, making it unnecessary to use shock to get a good coupling. Joining portions of a passenger train can be done at very low speed, so that the passengers are not jostled about. Rail equipment manufacturers such as Bombardier offer the Shaka coupler as an option on their mass transit systems and their passenger cars and locomotives. In North America all the trains of the Montreal Metro are equipped with it, as are new light rail systems in Denver, Baltimore and New Jersey. It is also used on light rail vehicles in Portland, Minneapolis, the Vancouver SkyTrain, and the Scarborough RT in Toronto. It also equips all the dedicated rolling stock used for the shuttle services in the Channel Tunnel. Maximum tonnage under 1,000 t. United Kingdom equals. Due to the rush to dieselize and electrify, the United Kingdom ended up with a variety of incompatible couplings and electrical connections. The latter were categorized as yellow triangle, blue square, and so on. This has nothing to do with the physical connection of vehicles. Coupling codes, as they were known, became relevant only if multiple working of locomotives or multiple units was required. Automatic buffing contact coupler equals automatic buffing contact coupler. Delmer equals. The Swedish-made Delmer coupling is a proprietary version of the Schaffenberg coupler, connecting both vehicle, pneumatics and electronics at the same time. The patented energy absorption DBOX technology allows coupling at speeds of up to 15 km per hour with no structural damage, and up to 36 km per hour with deformation but with the vehicles remaining on track. The patented DREX system provides Ethernet high-speed data connection at speeds of 100 Mbps. Ward coupler Ward coupler. Dual couplings and match wagons. Sometimes a wagon with one coupling system needs to be coupled to wagons with another coupling type. This may be needed when taking metro rolling stock from its manufacturer to the city where it is to be used. There are two solutions: use a match wagon, S, which has different couplings at either end, use a coupling adapter. Only some kinds of couplings coexist on the end of a wagon at the same time, because amongst other reasons they need to be at the same height. For example, in the Australian state of Victoria, engines had the AAR coupler, with buffers, and the chain mounted on a lug cast into the AAR coupler. A match wagon or match truck has different kinds of couplings at each end. If a pair of match wagons is used, a rake of wagons using coupling A can be inserted into a train otherwise using coupling B. A coupling adapter or compromise coupler might couple to an AAR coupling on a wagon, and present, for example, a Mutehopper coupler or rapid transit coupler to the next wagon. Such an adapter might weigh 100 kilograms. Dual coupling equals sets of carriages equals. Automatic couplers like the Janney are safer in a collision because they help prevent the carriages telescoping. British Rail therefore decided to adopt a Janney variant for its passenger carriages, with the coupler able to swing out of the way for coupling to engines with a traditional buffer and chain system. In New South Wales, sets of carriages were permanently coupled with a fixed bar, since the carriages were disconnected only at the workshops. Freight cars are sometimes coupled in pairs or triplets, using bar couplings in between. Articulated sets of carriages or wagons share the intermediate bogies, and have no need for couplings in the intermediate positions. Brake couplings. Couplings are needed for any continuous braking systems. Electronically controlled brakes electronically controlled pneumatic brakes need a method of connecting electrically adjacent wagons, both for power and for command signals, and this can be done by plugs and sockets, or by very short-range radio signals. Draw gear. A draw gear is the assembly behind the coupling at each end of the wagon to take care of the compression and tension forces between the wagons of trains. Early draw gears were made of wood, which was gradually replaced by steel. Janney couplers have the draft gear and a center sill to absorb the pushing and pulling forces. There is also a draw gear behind Tightlock couplers, SA3 couplers, CAKV couplers, Scharfenberg couplers, and other multi-function couplers. In the case of buffers and chain couplers, the draw gear behind the hooks, if any, will absorb the tension, while the side buffers will absorb the compression. Some couplers may not have a draw gear. Model trains. On model railroads, couplers vary according to scale, and have evolved over many years. Early model trains were coupled using various hook and loop arrangements, which were frequently asymmetrical, requiring all cars to be pointing in the same direction. In the larger scales, working scale or near-scale models of Janney couplers were quite common, but proved impractical in HO and smaller scales. For many years, the X2F, or horn hook coupler, was quite common in HO scale, as it could be produced as a single piece of molded plastic. Similarly, for many years, a lift hook coupler known as the Rapido and developed by ALll, a German manufacturer of N-scale model trains, was commonly used in that scale. The chief competitor of both these couplers, more popular among serious modelers, was the Matic, a magnetically released knuckle coupler developed by Keith and Dale Edwards, and manufactured by KD, a company they started. While they closely resemble miniature Janney couplers, they are somewhat different mechanically, with the knuckle pivoting from the center of the coupler head, rather than from the side. A steel pin, designed to resemble an air brake hose, allows the couplers to be released magnetically. The design of the coupler head prevents this from happening unless the train is stopped or reversed with a mated pair of couplers directly over an uncoupling magnet. An earlier, mechanically tripped version of the design had a straight pin extending down from the knuckle itself, which engaged a diamond-shaped mechanical ramp between the rails, which had to be raised above rail height when uncoupling was desired. Once the KD patents ran out, a number of other manufacturers began to manufacture similar magnetic knuckle couplers. Recently, an exact-scale HO model of the AAR coupler has been designed and manufactured by Frank Sargent. This design uses a tiny stainless steel ball to lock the knuckle closed. Uncoupling is achieved by holding a magnetic wand over the coupler pair to draw the balls out of the locking pockets. In O scale, an exact-scale working miniature version of the Alliance coupler was manufactured from the 1980s by GAGO Models in Australia. Since 2002 it has been marketed by the Arata Model Railway Company. European modelers tend to use scale hook and chain couplings. In British OO scale models the tension lock coupler developed by Triang is standard. This is similar in operation to the Meuchhopper type of coupling. Remote uncoupling is possible by using a sprung ramp between the rails. The design of the hooks is such that the couplings will not uncouple when under tension. When the train is pushed over the ramp, it will lift the coupling hooks as the train passes over. By halting the train over the ramp, it is split at this point. While it works well, it is often seen as ugly and obtrusive, and many British modelers prefer to retrofit either KD types or working hook and chain couplings. A recent development is an interchangeable coupling which plugs into a standardized socket, known as an EM362, and which can be easily unplugged as required. This allows the modeler to easily standardize on whatever coupling is desired, without individual manufacturers needing to change their coupling type. In 7mm scale working Norwegian couplings are now being manufactured by Zormzoodled in the UK. A comparison of coupler types was published in an introduction to couplers. Accidents. Different kinds of coupling have different accident rates. The Marula rail accident of 1926 involved the breakage of a draw hook leading to a runaway and then a collision. Draw hooks imply buffers and chain couplers. Round Oak rail accident Euro 1858 Euro coupling broke and rear of train rolled back. See also. References. Sources Norfolk and Western Railway Company v. ALll, 516 US 400, Eli Janney Euro the Janney coupler, Delma couplers AB Euro automatic and semi-permanent couplers, Vancouver SkyTrain Light Rail Network, Canada, Jane's World Railways, How Couplings Work, White, John H. 1978. The American Railroad Passenger Car. Baltimore, Maryland, Johns Hopkins University Press. ISBN 0801827434. OCLC 11469984. External links